Welcome to our read along with Dr. Pell in the book Discrete Perspectives in Mathematics. This is subsection 7.1.3, Time Complexity Properties. Okay, so this notation right here looks a little bit like less than or equal to, and that's kind of nice in some ways because this symbol is also used, just like an arrow, for a partial order. In fact, this guy can also be thought of as a partial order, but on some chunking. So we take our functions and we chunk them. Okay, so we take two functions, and if we chunk them together in some way, then this guy will actually be a partial ordering or develop a poset on those chunks. Okay, so first of all, let's just look at the functions in general. If you have this, so if you have okay, this means that, okay, so if this is asymptotic less than that, and this is asymptotic less than that, then transitivity should hold this is less than, less than, you could say, or asymptotically less than that. Is that, okay, so let's take a look at that. Okay, let's see why that's true. Well, first of all, this first statement means you could write it like this. All right, because if this is true, if it's asymptotically less than, then for sure the lim sup is going to be less than. Why is the lim sup going to be less than infinity if that's true? Well, that's because um, you already have the supremum in the mix, which is finite, and you may not ever get less than it, but if you do, it will go down, but at least it's going to be finite. And so if you have this, another way of saying that is the lim sup of this is less than infinity, which is to say eventually this guy is always less than some constant. And likewise, you can always say that h of n over j of n is always less than some other constant. So, and if you take the product of these ratios, that means that this is always less than the product of those two constants, which is to say that since it's always bounded above by some constant, that means g of n is asymptotically less than j of n. So it's definitely transitive in that way. Okay, clearly for any function, you have this. F of n is asymptotically less than f of n, so we got reflexivity. Okay. It's less than itself because f of n over f of n is 1. Okay, and that would be the bound itself. Okay, so now, but in order to have anti-symmetry for a poset, we're going to have to merge things, and that's where the function classes come in, or equivalence classes come in functions in order to make the chunking, so to make a poset. Okay, so in general, if we ever experience this idea, if f is asymptotic less than g, and g is asymptotically less than f, that's like a loop around. We don't want that for an anti-symmetry property of a poset, so we need to merge all these guys together in order to be okay still. So basically, we do that. Okay, so if we ever have this happening, just merge them together, then we have a poset. The fibers of this merge are equivalence classes with respect to that. Okay, so anything in the equivalence class of this can equivalently express the asymptotic order of a function. So if something is asymptotic less than something else, and something is asymptotic less than the other thing, back and forth, meaning the ratio one way or the other way is bounded by a constant both ways, then we can say that asymptotically, they behave the same in the way they grow. Okay, so let's find an equivalent way to express this. Okay, big O of that expression. So notice that this is the solution to that, and Planck log both sides. We can basically change the base formula here. I described how you can get it without knowing it before, but you can rewrite this as a change of base of log of n over a constant. The log of square root of 2 is a constant. So what we end up getting is that we can think about, so since this is just equal to this times a constant, that actually will give you that this is asymptotically equivalent to this guy. Well, log of n is asymptotically equivalent to log base square root of 2 of n. It works both ways. All right. So we can think of them the same way. So really, well, that's interesting. So the base didn't even matter because it just, if I change a base form, it just adds in a constant. Right here. So really we can, if we're talking about the asymptotic growth or size of in this algorithm, we could just simply say log n. We could just simply say the Euclidean algorithm computes the greatest common divisor, has time complexity O log n. We could just say that and be done. Instead of thinking too carefully about the base. Now there's different ways. I mean, that's if we're thinking about number of lines, but if we're thinking about elementary one-digit operations, here's a little description based upon the what we had going on before. Essentially, notice this is somewhat interesting in this computation. So you can look at the details that I write out, but essentially it looks like we're throwing O's around quite a bit in the addition process, from here to here, and adding and pulling them out, and distributing and throwing them in and so forth, just kind of loosely with asymptotic sizes. If you actually look at the definition of O, and even even thinking about ratios being bounded eventually, like we were doing up there, it actually works quite well to show that the big O notation can pass in and out of addition and even multiplication. So if you have some idea that's this size in order and that size, if you add them together, it's actually going to be of note it's going to be the big O of the addition. And look at the n squared actually goes off because n squared plus n cubed is asymptotically less than n cubed itself. So kind of like the bigger power here wins. And you have the same basic idea. And that concludes this subsection. Thank you for watching.